Hello everyone, and welcome to the 8th lecture on the this course, that is Introduction to Remote Sensing. And in this particular lecture we will be discussing different multispectral scanners and different imaging devices which are very popular nowadays. If you remember that we discussed in previous lectures that two types of remote sensing is possible. One is passive remote sensing and then active remote sensing. So, the sensors are also accordingly, and there are two major categories of sensors. One is the passive sensor, very popular one, which we will see one by one, and then active sensors. Now, both of these passive and active sensors, one are the non-scanning and scanning type. Similarly, in case of active sensors, some of them are non-scanning and might be scanning sensors. Then when we come for in this non-scanning, we can have non-imaging sensors, we can have imaging sensors. Again, in case of scanning, mainly imaging sensors. In case of non-scanning, non-imaging sensors and scanning, imaging, and different sensors are there. So, especially if we take the sensors which are passive and then like microwave, passive microwave radiometers, or sensors are there which are passive sensors, non-scanning, non-imaging. There are some satellites like GRACE and others which are in they work for the gravity properties of the earth. So, there are non-imaging, non-scanning sensors. Similarly, in case of non-scanning imaging sensors, you are having cameras, maybe monochromatic cameras, natural color infrared, color infrared, and the others. So, these are the sensors which are on board of different satellites. Then scanning sensors are also there, like imaging, image plane scanning, TV camera, solid scanner, object plane scanning, optical, mechanical sensors, microwave. So, initially when remote sensing started, we had these optomechanical scanners. Now later on we are having non-scanning imaging sensors like all these. Then in the category, under the category of active sensors, two types, scanning, non-scanning. Under this non-scanning we are having non-imaging, so like microwave radiometer, microwave altimeter, and so on. Similarly, in case of active scanning, imaging, object plane scanning, real aperture radar or synthetic aperture radar. So, radar remote sensing, the examples we saw about like radar set, or our Indian example RISAT, NVSAT, and Sentinel, all they work in this synthetic aperture radar. That means the sensors is active, the sensor is scanning, and it is basically synthetic aperture radar having object plane scanning. And there might be this is scanning imaging, but image plane scanning. So, these are the different types of sensors can be there, but the most popular one are these ones, optomechanical, they were there, then synthetic aperture radar and other microwave sensors. We will see examples of these different types of sensors associated with different types of satellites in initial stages of development of remote sensing and later. As you can see that in case of active remote sensing, basically the pulse is sent by the instrument or on board the satellite, and then whatever is returned back, it is recorded, and this is how you acquire the data of radar data or active remote sensing data. Whereas in case of passive remote sensing, the main source of radiation is available through, or energy is available through the sun, and then we record different signatures having different kind of reflection, emission, and so on and so forth. So, two major types, active remote sensing and passive remote sensing. The 80-90% of remote sensing is which we are doing is passive, but nowadays because of SAR interferometry, active is also very popular. We will see the examples how these have been applied. Active sensors, in different part of spectrum, EM spectrum which are there, especially the radar one, the synthetic aperture radar, side looking aperture radar are there, and of different bands, K, X, S and L band, K, Ku and C band. C band is very popular, L band is very popular among radar remote sensing, also X band, but the C band example are many more. There are some other parts of EM spectrum, but may not be having satellite sensors on board, but maybe through lower atmosphere or through aircrafts can be acquired data. Whereas in case of passive sensors, we are having a most popular one are visible near infrared spectrometers are there in this range, that means the 0.4 micrometer to 1.1 micrometer or 400 to 1100 nanometers. Microwave radiometers are there, and then thermal infrared sensors are also there, which is having between 8 to 14 micrometer. So these are all passive sensors which are shown in blue color, and these red one are the active sensors which are shown, and part of EM spectrum, both frequency based and wavelength based is also shown here. So as mentioned that the passive sensors, the sun's energy is either reflected in the visible length or absorbed and then re-emitted in the thermal infrared wavelength. And the remote sensing systems which measure energy that is naturally available are called passive sensors. Passive sensors can only be used to detect energy when naturally occurring energy is available. And for all reflected energy, this can only take place during the time when the sun is illuminating the earth. So only that means it is possible in the daytime in case of visible near infrared images, but in case of thermal infrared that can work in night time as well, and there is no reflected energy available from the sun at the night, and the energy that is naturally emitted such as the thermal especially in the thermal infrared portion of EM spectrum can be detected day or night time as long as the amount of energy is large enough to be recorded, because during this emitted energy is not relatively very large, and therefore it is one has to get that much of energy so that it can be recorded by the sensors which are around 850 kilometer deep in space. This is again passive example of passive remote sensing, and especially with the Landsat 8 OLI series is given, and that different bands are collecting information, reflective data at different part of EM spectrum, like band 1 between 0.43 to 0.45, and like band 7 2.11 to 2.29. And different channels the data is collected. One may create a false color composite. In the previous lecture we have discussed in length how false color composites are created, what are the advantages of false color composite and why basically false color composites are created, and ultimately you can create such colored false color images which are very useful for image interpretation. This we have already covered, that you involve green channel, red channel in a standard false color composite, and near infrared channel assign blue, green and red color respectively, and ultimately you end up with a standard false color composite image. Now in a false color composite image the same area may look like this, but in a thermal infrared image in the night time the same area may look like this, like an X-ray kind of thing. So altogether different appearance of Earth's objects in different part of EM spectrum, also in daytime and night time. Whereas active sensors provide their own energy as mentioned earlier, which are having their own source of energy. They send the energy pulse, so sensor emits radiation which is directed towards the target to be investigated, and these are also called ranging devices. And because the radiated reflected from that target is detected, the return beam is detected and measured by the sensor. That is why they are called your ranging devices. Advantages of active sensors, which includes the ability to obtain measurement anytime, because the energy source is within your hands. So whenever you want to measure, you send the pulse, and whenever it will return, you record it and you measure the distance. So so that is the advantage, that ability to obtain measurement anytime, it is day or night time, also regardless of time of the day or season. Another advantage of this thing is that in microwave region, where these most of the active sensors are there, you have the advantage that the wavelength is much larger. So the clouds, gas particles, dust particles will not create any scattering or absorption, and you get a very nice clear pictures in this through these radar remote sensing satellites. Active sensors can also be used to examine wavelengths that are not sufficiently provided by the sun, such as microwaves, or better control the way target is illuminated. So the way we want to illuminate a target, that can also be designed or decided by the sensor or operator of that instrument. However, the active sensors require generation of a fairly large amount of energy to adequately illuminate targets, because a satellite on board, the sensors on board of a satellite, especially I am talking radar satellites, then large amount of energy is required so that images can be acquired by that. So that is one limitation of this thing. And most common active sensors in radar range of EM spectrum are synthetic aperture radar, as mentioned, like NVSat, like Sentinel, like RadarSat, RISAT, all they use this one. Example of our own Indian remote sensing satellite of part of Tripura from RISAT 1, that is the image acquired on 22nd September 2012, and as you can see that there is no effect of any effect of atmosphere, and especially in this part of the country most of the time you are having clouds, but in microwave region in active remote sensing cloud will not affect, and therefore you see a complete clear terrain, and all geological structures and plunging folds and plunging antiforms, synforms can easily be identified on such images. If you go for corresponding images in passive satellite data, like in visible channels or near infrared, in near infrared you would find that these parts are fully covered with vegetation, so a masking effect you will see, and cloud problems are also very common in this part of the country, whereas in radar remote sensing clouds will not create problem, and all these geological structures can be identified very easily. So there are various advantages of having active sensors. Now there are multispectral scanners or sensors systems are there. We started with the MSS multispectral scanner with Landsat 1. So these scanning systems are employed or put on a satellite, and which covers a narrow field of view and sweep over a terrain to produce an image. And there are two types of multispectral data or sensors are there, which acquire data either across trace scanning, or which we call whisk broom, like for example in case of Landsat sensor on the Landsat, or along track scanning, which was introduced through by Spot and later on by Iconos. So we call them as push broom. So whisk broom and push broom scanners. We will see in details what are the advantages and disadvantages of these two types of scanning devices in passive remote sensing. Across track, that if satellite is overpassing like this, the the orbit is like this, then across track the scanning is done, and pixel by pixel there will be a rotating mirror, and that acquire the images. So these using a rotating or oscillating mirror, such systems can scan terrain along scan lines that are right angles to the flight line or orbital path, and this allows scanner to repeatedly measure the energy from one side of the platform to another. So once the satellite moves, then it goes to the next line, then next line, and likewise it keeps scanning and recording the data or sending data to the earth stations, and this way the data is collected within an arc below the system, typically of some 90° to 120°. But these may introduce some complications or some problems which we will see little later. Incoming energy is separated into several spectral components that are sensed independently, and non-thermal wavelength component is directed from getting through a prism or a different grating, and split the energy into continuum of visible, ultraviolet, visible and near infrared bands. At the same time, the dichroic grating disperses the thermal component of oncoming signal, which is a constituent wavelength. There were a lot of complications were observed with such kind of scanning devices. An optomechanical scanner is a multispectral radiometer by which images can be recorded using a combination of motion of platform and a rotating or oscillating mirror scanning perpendicular to the flight direction. So because of this oscillating or mirror rotation, a lot of problems were observed, especially in the Landsat and in the first generation, that is Landsat MSS or Landsat 1, which had the MSS sensor. These optomechanical sensors are composed of an optical system, a spectrographic system and a scanning system, detecting system and then reference system. So multispectral scanner MSS, I gave the example, thematic mapper of Landsat and a NOAA AVHR are also example of optical mechanical scanners. Another type of scanners, not across track, now along track scanning, which is a across track system. Along track or push broom scanners record multispectral image data along a swath beneath the aircraft. So you are having a array of sensors arranged like this, and you acquire line by line, and this has made things very easy. So also similar to use of forward motion of satellite to build up by an image by recording successive scanning lines that are oriented at right angles to the flight direction. However, there is a distinct difference between along track and across track system in the manner which each scan line is recorded. Here an array in along track system, there is no scanning mirror, no oscillating or moving object or optomechanical devices. It is a solid state kind of thing. So instead of a linear array of detectors used, and which scans directly parallel to the flight line, and array normally consists of numerous CCD devices which are positioned throughout this one. So if I give the example, like you are having a CCDs are all situated here, and this is the flight track or orbital track of your satellite. So it keep moving and keep scanning simultaneously all along the line. So because it does not involve any oscillating or optomechanical devices, that is why the images are of high quality. So each detector element is dedicated to sensing the energy in a single ground resolution cell along any given scan line. This is, and along track scanning devices are nowadays very popular and common in most of these new satellites. So the examples are shown here, and that a linear array or this push broom, whisk broom examples are shown, and in hyperspectral area then again the arrays are used, so that along track scanning devices are used. whereas in this one this is rotating mirror. So different channels are different pixels are gathered here, whereas here the entire line or the swath is covered in one go. So different way of collecting the data. There are advantages with along track scanners. The linear arrays provide the opportunity for each detector to have a longer dwell time or residence time over which to measure the energy from each ground cell resolution cell. So that is the advantage with along track scanner, enables much stronger signal to be recorded, a greater range of levels of signals can be sensed. And this concept, array concept and along track scanning has allowed us to move from relatively coarser resolution data like MSS, which was an optomechanical across track scanning, to along track scanning systems, which has allowed us to go for higher and higher spatial resolution. So this is because of it enables us for a stronger signal to be detected by these sensors, because stay time while a satellite is moving is much more compared to across track scanners, and this leads to better spatial and radiometric resolution. In addition, the geometric integrity, radiometric resolution, basically here the meaning is the quantization of the pixel. So instead of having a 6-bit image, 7-bit image, it is possible to have 8-bit, 10-bit, even 11-bit images. So the higher radiometric resolution, better spatial resolution became possible because of along track scanning systems. In addition, the geometric integrity is also better in case of along track scanning devices. So that is why they became very popular in many of sensors on board of different satellite. Further advantage is the geometry along each scan line is similar to that of characterizing an aerial mapping camera, because CCDs are solid state, there is no moving part, and they are generally smaller in size and weight and require less power for operation. So another advantage is that they are lightweight and they are compact, and the weight of a sensor on board of a satellite is also less. It requires less power for operation. However, there are one disadvantage to push broom scanner is need to calibrate many more detectors, because instead of one detector in case of across track you are having arrays of detectors, and now these detectors should perform uniformly, and therefore before launching of any such sensors, such scanning devices, their calibration, very high quality calibration is required. Otherwise, if two adjacent CCDs are performing differently, they will acquire data differently and your image will have a lot of problems. This problem was recently observed in case of Landsat 8 images, and then the corrections of such images becomes really very difficult. So this brings to the end of these different types of multispectral scanners, optomechanical devices, linear array devices, their advantages and disadvantages. Thank you very much.